Thank you, Shane. We'll have the opportunity to thank Shane more appropriately in the coming days, because his work has been amazing for this conference. Welcome, everybody. I am extremely happy that this is happening. We didn't know if this was going to happen until very late. I am delighted to introduce Jakub Dotlac as our first speaker, and first invited speaker for AmLab 28. And Jakub is exceptional. Where is Jakub, by the way? Oh, you are there, okay. You never know. Jakub is an exceptional researcher in several ways. His expertise ranges from inquisitive semantics. And when you know that you're not sure about the meaning of inquisitive in something like semantics, you know that that must be quite specific kind of knowledge. So when you tell me dynamic semantics, I'm with you. Inquisitive, I need a little introduction. But his expertise in semantics is in depth, and is having somebody who has in-depth knowledge of formal semantics and experimental psycholinguistics and cognitive modeling. That's quite exceptional. And so Jakub's early work focused on formal semantics and ranging from interpretation of pro-anaphora to distributivity and the scope of quantifiers, among other topics. Jakub conducted this work at the University of Utrecht, where he got his PhD, and early on at ZAS in Berlin. I believe it's during a 2-year stay at the University of California, Santa Cruz, that Jakub's work started focusing more on experimental psycholinguistics and cognitive modeling. It's in this time that I believe Jakub began a long-standing and productive collaboration with Adrian Brazoveanu. From this time on, as I said, Jakub's work focused more and more on experimental psycholinguistics and what makes his work exceptional, incremental semantic processing. This type of work includes work on interpretation of implicit causality, comparatives, degrees, quantification, and numerals. In more recent years, this work, like Jakub, also in collaboration with Adrian Brazoveanu, to produce groundbreaking work on computational cognitive modeling and Q-based retrieval of semantic representation. So this line of inquiry, as I believe we will hear shortly, focuses on the incremental processing of semantic representation, like presupposition, which involve memory retrieval. So when we process a sentence such as Jakub went to AmLab and Amanda did too, the interpretation of this additive to requires that we retrieve an antecedent from memory. While a lot of work in our field has been devoted to retrieval of syntactic information and cognitive modeling of this retrieval, much less work has been devoted to retrieval of antecedent of presupposition and semantic information. And this work obviously involves assuming representational levels of assumed, say, by discourse representation theory, which have always claimed to be cognitively based on cognitive real assumptions, but could not quite back these assumptions until I believe you start working with cognitive modeling. And so these are the reasons why we thought Jakub would be an excellent invited speaker for our conference. So without further ado, Jakub Dotlac.
Okay, can you hear me fine? Can you hear me in the back? Okay, perfect. So thanks a lot for inviting me. Thanks a lot for organizing this conference. And even more, thank you for organizing it in a hybrid way. So I'm super happy that I'm presenting it here to you, this talk, and I'm doing it here in New York and not in my attic, in my house. Okay, so this will be about cognitive modeling, and the talk will be about cognitive modeling given theoretical considerations. And in cognitive modeling, one especially fruitful line of research was rational theory of cognition. And rational theory of cognition could explain various phenomena. And one particular successful account was rational theory of memory, developed by Anderson in the beginning of the 90s. And this rational theory of memory was used for particular cognitive model, or what we call cognitive architecture. And that architecture, it's called ACT-R. And so it's an acronym, the name, so it stands for Adaptive Control of Thought, Rational. And that rational, that was what was brought into by this rational theory of memory. Now, ACT-R was used in linguistics and psycholinguistics to model psycholinguistic data, especially processing data. It was used in sentence processing models in large, but it was also used quite specifically for something that people use often, and that is queue-based retrieval models. So now, when we look at memory, you can think of two ways how sentence processing interacts with memory. So on one way, we recall dependencies when we process. And here I have some examples of dependencies. So when you look at the forced red sentence, can you see it? Yeah. So students usually know the teacher. When you get to know, you have to, in order to be able to understand the sentence, you need to recall what was the subject of that sentence, right? So you need to know, oh, okay, so the subject was students, therefore the students are the agent of knowing. And you also need to recall that information in order to be able to get the right form for the verb. There is a second example of dependency, right? So the man told Sue about himself. We have himself here. And again, in order to be able to correctly understand this sentence, you need to recall, oh, what was the antecedent of himself? Oh, man, right? So we need to record that information. And so that's one way how we can think of memory playing a role in processing. Now there's another way, and that is we need to be aware of parsing rules. Right? So we have to have grammar knowledge, and we are also recalling that when we are doing sentence processing. So for example, for these cases, we have to recall information like, oh, subjects usually precede verbs, objects follow verbs, reflexives have to have antecedents, and so on. And so you need to have all that information. Now, when you look at cognitive modeling accounts, you see kind of discrepancy in the way we treat these two phenomena that are related to memory. So we have memory-based explanations how dependence affect processing. So that was that case one. Yeah, so we have models like queue-based retrieval, direct access model, and so on. So some of these were inspired by this rational theory of memory. But all of these models basically assume they build in some, or they make use of some kind of assumptions about memory. And then we have a completely different type of explanation when we look at how the application of parsing rules, so the case two, how that affects processing. And in particular, in these cases in cognitive modeling, we usually go to some kind of information theoretic metric. So it could be surprisal theory, it could be entropy reduction, and so on. Right? So not only do we have not one general theory, but we don't even have like we don't even have the same attitude towards these two types of memory phenomena. We deal with them in a different way. And so that's not perfect state of affairs. Yeah? Now, so there have been attempts to actually create one overarching theory for both aspects of processing. And so one such recent account is lossy context surprisal, developed by Roger Levi and Richard Futrell. And it basically took the second part, so if I point, it took this surprisal theory, and it said, oh, okay, we can expand it. We will actually include some kind of memory assumption into that model. We will assume, namely, that we are forgetting things. And by doing that, it could actually expand to the phenomena that are normally covered by memory-based explanations. Right? So it moved from this part to that part, and it was also able to capture dependencies and processing of that. So in this talk, I will present a different take on the issue. So I will also create just one overarching theory for both aspects of processing, but I will go in the opposite way. So I will start with actually memory-based explanation, queue-based retrieval, and I will move it to this part and will explain what normalized surprisal theory does. Yep. I should say I'm not the only one doing that, so there are some other accounts, but I will not have time to compare my accounts to these other accounts. So there are some accounts in computational linguistics that were popular around the year 2000, and there are some accounts also in cognitive modeling, and I will not be able to talk about this. Okay, so this is the structure of the talk. So I will start talking about rational theory of memory. Then we will move on from queue-based retrieval of dependence to queue-based parsing, and we will test the model. Right, so I should maybe say this. So this idea basically to transferring this queue-based retrieval from here to here, I will call that queue-based parsing throughout the talk. Okay, so I'll start with the first part, the rational theory of memory. So when you have rational approaches, you always have to start with like, so what's the goal of that particular subsystem? So in the case of memory, arguably the goal is to basically give us the information, or what I will call chunk, that we need at the moment. And we can think of chunks of some like very primitive pieces of information. So it could be something like this. So this is, for example, chunk being like, so I'm organizing a party and I need to know what kind of food I should order. So I know that Bob is coming to the party, and then I know that he likes a hamburger, right? So that and I could have another chunk and another chunk in my memory like this. And okay, so okay, what I need to get out of my memory is the most probable chunk, a chunk that will be useful. And so I'll be talking about this PI, which is need probability of chunk I. And so the basic intuition of this rational approach is that the higher the need probability is, so the more I need something, the more likely we will retrieve that piece of information very fast, and it will be easy to do that. Yeah. Okay, so I'll go through a bit of details. There will be a little bit of math. I'm just doing this to basically build the thing ground up. There will be just, so there will be a bit of math now. I promise it's only 3 slides, and I will try to do them quickly, and then we will move on to, to something more interesting. Okay, so we'll be talking about this probability that some information is needed, and we can conditionalize it on various pieces of things. So here I'm conditionalizing, or people often conditionalize it on these pieces of information, namely on the history, so of the past usage of that information, and the current cognitive context. So what is my state at the moment? And we often don't talk about these as just probabilities, but for mathematical reasons, we describe these as log odds. So this IC stands here for not needing that piece of information, not needing that chunk. So this is like odd of, here in the numerator, I have the probability that I need the chunk, given some history and current cognitive context. And in the bottom, I have probability that I don't need it, given the history and cognitive context. And we call this activation, this bit. And then we can, using some rules of conditional probability, we can split this up into 2 other parts. So we have this first part where we relate needing chunk to history, and we call that base level activation. And then we have this second part, which we relates to needing the chunk to the current cognitive context. And here, by the way, I assume I make some independence assumptions about history and cognitive context. Okay, so this is the basic formula that gives us this rational theory of memory. And I will not be talking about this first part, about this base level activation. So it's mainly used to basically, so it suggests that we sort of track frequencies of objects, and we use that to guess when we will need the information about the object in the future. I will be only talking about spreading activation, which is at the heart of queue-based retrieval. Okay, so this is just spreading activation written one more time. And we can sort of break it down into a bit more elaborate information. Namely, we can say, so my current cognitive context consists of some cues, and the spreading activation is the sum up of log of using those cues. Now we have some conditional probabilities here, and particularly in the bottom, we conditionalize on not needing some chunk. And most of the time, we don't need a particular chunk, so we will just ignore this conditionalization. And that gives us the final formula, which is this, and that can be rewritten like this. Now, in the bottom part, what does it say? So it says, so we sum up, we look at all the cues that we need, and we get the log of, do I need some particular chunk given the cue, and divided by just, do I need the chunk no matter what? Yeah? So in some way, we can sort of simplify this as follows. So we can think of this, do I need the chunk? So if all the chunks are equally needed in my memory, then this would be just, so the probability that I need one particular chunk is 1 over all my chunks in memory. And do I need a particular chunk given a value, then that would be 1 over chunks that have that value. And that gives us the final formula, which is what you see here on the bottom, and that's often used in Q-based retrieval. Basically, this is now we derived what you often see in Q-based retrieval, and that is we sum up. So we look at all the chunks, and we do the log of our size of memory minus what is called log of fan, where fan is all the chunks that we have in the memory and that have the same value. So here I have the picture at the bottom that might help with the intuition, right? So this was math, but just with the intuition. You can think of our memory in this framework as like sea of darkness. And you have light bulbs in there, so those are the chunks. And you are trying to find the bulb that shines the brightest. And the bulb that shines the brightest, that's the most activated light bulb. And that's the light bulb that we most likely need. Right? So you don't need to go through all the light bulbs. It's enough that you find the one that shines the brightest, because that will be the one that you need anyway. And now, so the light comes from some power. And particularly the power here is driven from this current cognitive context. So we can think of like, we have this current cognitive context, and that powers the light bulbs that have the same value. But if more light bulbs have the same value, then this power is spread over those, so they will shine a bit less. So that basically gives us already what is called fan effect, or in linguistics, it's called Q overload effect. So here's an example. So we have this, we are trying to recall whether there's someone going to the party and whether that person likes ice cream. So here on the right side, we have the current cognitive context with, cues, party and ice cream. And this is our memory, and we are trying to retrieve some information from that. And so we spread activation to this chunk in memory, right? So it lights up, and we will likely retrieve it, and we will retrieve it fast and easy. And you can compare that with the situation where we get so-called fan effect or Q overload effect, where you have again Qs, but you have Q overload because one of the Qs is shared by multiple chunks in your memory. So in that case, you still spread activation to both, but it will be shared, so it will be a bit smaller for each of those. So in that second case, we will have a bit smaller smaller activation than in the first case. So this is so-called fan effect, often observed in cognitive psychology. And we also observe it in linguistics, so where it's called Q overload mainly. So here's one example from Van Dijk's study. So here we have a verb or verb phrase was complaining, and we are trying to recall the animate subject to get the interpretation right for here. So the animate subject is here in the board, the resident. But there is this interfering element, the dangerous neighbor, right? And so in 1A, the dangerous, we have this interfering element, the dangerous neighbor, which shares this feature of animacy with the subject. And in 1B, we have the dangerous warehouse, where it doesn't share the animate feature with the, resident. So we expect that 1A somehow, when we are retrieving, we should retrieve slower, and we should observe more problems than in 1B because of this fan effect. Overload. And indeed, that has been found, and that has been replicated in quite a lot of studies. So here's some graph from meta-analysis which shows that there is, when you have this sharing of features between the distractor and the target, you get this slowdown effect observable in processing studies. Yeah. And we have sort of the opposite effect, which is called the So we have sort of an opposite effect, which is often in agreement attraction. And in here, so we have a verb, or verb phrase, where rusty, and we are again trying to retrieve. So we are trying to again retrieve the subject, and this time it should be the subject that's in plural. Now notice the subject doesn't match the plural requirement, neither of those in 2A and 2B. But we have this distractor, which in one case it matches the plural requirement, right? So it has the cells, so that would match the plural requirement, but it wouldn't match the subject requirement. And in this case, when we have this partial match, so of the distractor, we actually get speed up, and that has been again observed many times. And so that, again, that's something that's predicted by this theory. So we can visualize it like this. So we have this where state, that's our current cognitive context. We spread activation from subject feature to key, and also here. But in 2B, we have this case where we also spread activation to plural. And now that means that this element will have higher activation than this element. And because of that, this will be retrieved faster and easier. And if, for example, there is some weight on this queue, and the weight is higher than the subject weight, then this will actually be faster processed than 2A. Okay, now I'll actually go from queue-based retrieval to queue-based parsing, and so we'll see how that goes. Okay, so we talked about, so I introduced queue-based retrieval, and I showed you how it can be used to basically predict some data about dependencies, so like subject-verb dependencies. Okay, and so now what about parsing? So now we want to move on. So how could we deal with actual parsing? So syntactic structure building, so the fact that we not only know dependence, but we can actually parse sentence and understand it. So we will assume here that it's exactly the same memory retrieval process. So we just recall our past knowledge of how we parse a particular sentence. So we can think of parsings as transitions between syntactic structures, and this gives us actually a class of parsers, which are called transition-based parsers. And we will assume that readers basically store previous transitions in memory. And I will just quickly walk you through one example. And then we will assume that readers can recall past transitions using the rules of queue-based retrieval, and that will be the queue-based parsing, right? So now we are transferring this idea to queue-based parsing. So for transition-based parsing, we will assume that there are two pieces of information. There will be some stack of trees that we have built. There's like upcoming words that we need to have. And then the parser's job is basically to just move us from this current cognitive context, which will be consisting of this stack of trees and the upcoming words, and to some action. So it should basically tell us what we should do. And it can tell us that we can either shift a word or build a tree structure. So just to give you one quick example, so here we have a sentence like a boy dances with, I assume, this tree structure. So we have subject, a boy, and dances, a verb phrase. And this is how it could go. So we have upcoming words, a boy dances. Then in order to build this tree structure, so we first shift the first element and we build this subtree. Then we move the second element and we build this subtree. Then we put them together. And then we shift the third element and we build this subtree. And then we just merge all those together. Right, so we have like these steps where we are proceeding, basically, we are replicating the tree that we want to get step by step. And now you can, okay, so this was just a silly example. And now we can ask, okay, so what happens when you have something like a boy sleeps? And let's say we have this is our current cognitive context. So we sort of build up this. So how do we decide what to do? And this is where queue-based retrieval kicks in. So we just basically do queue-based retrieval, but now on these parsing steps, now on these transitions. And we could think of various queues that could be used here. So we could have labels of tree structures. We could have some information about upcoming words and so on. And so these all could be our queues for processing. Okay, so just to step back, so what we did is, so we built a model of parsing using this idea of the rational theory of memory, which is implemented in queue-based retrieval. Now, this theory has been used for other aspects of processing, for retrieval of dependencies. And so because we are basically using just the same framework for both, we have a general framework for memory and sentence processing, at least as far as these two phenomena are concerned. So, and that means that we can now take this model for full sentence processing, and so we can build up sentence processing, at least as this is concerned, within one and the same model. And so this gives us predictions. And so one of the predictions, so I'll just give them here now in abstract and we will see them more practical. So in abstract, so for example, we can expect something like fan effect could appear in parsing, right? So this is just the fan effect that we saw before. So we have this spread of activation of the hamburger feature. And we could expect something like that in parsing happens as well, right? So we could, for example, imagine that if we have some spreading activation of, say, noun feature, that might, so noun queue, that might be a bit harder to retrieve that piece of information than when you have some more specific queue that's unique for some particular chunk. And you could also imagine that there's something like grammatical illusion in this queue-based parsing. So here again, this is the repetition of queue-based retrieval and how it predicted this illusion, this agreement attraction phenomenon. Right, so we had this case here where we had a bit of speed up here because we had this boost by the plural activation. And you could imagine something like that is also going to happen in parsing. And it is you basically, if you are in a case where you have multiple queues matching, that would boost your activation. So that will mean that that parsing step or that parsing will be processed faster than when you don't have it. Yeah. Okay, so I went through the first two parts, and now I will start testing the model. Yeah, so now after 20 minutes, I can finally get into the interesting stuff. 25 minutes maybe. Okay, so I will look at 3 case studies. So I will try to model data using the ideas that I just talked about for Grodner and Gibson study, for Adrian Staub's study, and then for some corpus data. All these data are processing data, so it's either self-paced reading or eye tracking data. And so why did I pick those 3 cases? I'll talk, well, or those two cases, I'll talk about corpus in a minute. So what's interesting about those studies is that they somehow combine different types of retrieval. And that's perfect for a model like this because it basically assumes one and the same model for all types of retrieval. So you can basically model now all those types of retrieval within the same thing. So it's good to match it against that type of data. Okay, so Grodner and Gibson study. So this is self-paced reading study where we have some matrix subject, the reporter here, and it's modified by a relative clause. And the relative clause could be either subject relative clause or object relative clause. So in 5, we have the subject relative clause, who sent the photographer to the editor, right? So who is the subject of send. And in 6, we have the object relative clause. So who the photographer sent to the editor, so who here is the object of send. Okay, we will model reaction times from this self-paced reading study for these 6 regions of interest that are underlined above. And again, so why we are doing that? Yeah, that's important. We are just not picking some random study and try to model that. So we are doing this because it has actually been argued that processing difficulties observed in object relative clause, so there are some processing difficulties. So the processing difficulties observed in object relative clause are actually due to 2 things. So due to the fact that we need to do dependency resolution, right? So we need to resolve, when we get to send, we need to resolve you know, who has been sent, so that it was the reporter. So that's the dependency resolution. And at the same time, there is also processing difficulty due to the expectation. So when we get into this sentence in 6, we are actually, by default, we are sort of expecting that we should get the subject relative clause, and that's not what we are getting here, right? So we have 2 different sources of processing difficulties. And so normally you would actually take 2 different models to model this kind of data, right? So you could do the dependency resolution in queue-based retrieval, and the other thing you could do in surprisal theory. But now we can actually do within one model. And so we will just take queue-based retrieval. In one case, it will apply to dependency. In another case, it will apply to parsing, and we will get the results. Yeah. Okay, so this will be our model. So we actually will try to model the whole thing. We will not, we will not shy away from details. We will actually try to model the whole processing, so the whole reading procedure. And so for that, we will actually assume that there are some steps, sort of procedural steps in the processing. So on each word, we will assume that people attend word and they retrieve lexical information, retrieve parsing steps. So this is our queue-based parsing here. Then they might retrieve dependent, so whatever was present before, in case there's a gap. So like they're retrieving the reporter when they get to the verb, and then they will press key and move visual attention to the next word. And we will make some, so we will assume that each of these processes takes the R amount of time, and there might be also reanalysis if you get into the wrong structure, and that will also take the R amount of time. And then we will assume some default ACT-R values for the rest. Okay, so we need to now do the basically this reading mechanism, and so for that we basically need to construct this queue-based parsing. So how do we do that? So we use some techniques from computational linguistics. So we will just take, basically we will take the memory of some particular tree bank, in this case span tree bank, and it will represent our parsing memory. Right? And we will use that for the retrieval. And because we have some free parameters in the model, we will have to estimate those free parameters. So it's not important for you, these free parameters. There's one thing I should mention is, so we have two parameters here, so this big F and small f, and they modulate the retrieval time given the activation. Then we have some parameter that will modulate the queues that boost the activation. And then our last parameter is this R parameter, which modulates the amount of time that each of these processes takes. Right? So we will basically fit the data to the model, just playing around with these 4 parameters. And notice that the only thing that we hand coded is that the procedure goes in these steps. That's the only thing that we hand coded. So the rest actually is data driven. So the rest actually comes from the model itself. Okay, so it was some kind of Bayesian model that would fit the data. That's not so important for you. You can ask questions about this later. And so now, crucial bit. So actually, when you look at the behavior of the parser, so you can actually see when you look inside, is that when the parser gets to the reporter who, this queue-based parser actually starts guessing that this will be the relative clause that is subject extracted. And then when it gets to the reporter who the photographer sent, then it will actually start guessing that this is the relative clause that is object extracted. So it's, in other words, the parser has the active filler strategy. That's not, again, that's not hand coded. That's just derived by the fact that we do this. We store these parsing steps, and we do queue-based retrieval on top of them. Okay, and here is the fit to the data. So we basically play around with the parameters in the Bayesian model until we get a good fit, and then we can check how good the fit is to the data. So these are in yellow, what you see are the actual reading times that were observed in the study. So the triangle here, that's the mean reading time, and the bars are 2 standard errors. And the blue are the model predictions when we fit those 4 parameters. And so on the top part, you have the object relative clause. On the bottom part, you have the subject relative clause. And so this would be who, what was it? Okay. Who the photographer sent to the, and this would be who sent the photograph to the. Yeah? And okay, so as you can see, the fit is actually pretty good, right? So the bars overlap most of the time pretty well. Also, the model gets things like it actually slows down here. So in the object relative clause on the verb. So it gets the general, and nothing like that happens on the verb here. So it gets the general pattern right with very little hand coding. So all this basically comes from what the model assumes and how queue-based retrieval proceeds. Now, it's actually not so interesting on its own to have a model that fits. It's more interesting to have a model that fails and then to compare the two. So that's what we will do here. So we will basically take the same model, but we will switch that active filler strategy off. So it will not be guessing that the gap is coming up. There are some technical ways of how we do that. We basically train the model with the knowledge of what's the upcoming word, and then it will stop doing this active filler strategy. And what you get there is then much worse fit. So you can notice here, then suddenly, the model is much less sure. So it has much wider bars. It doesn't know that well how to fit. And it also doesn't even fit something. So for example, here on the verb in the object relative clause, it doesn't even fit the mean of the observed data. And we can also play some more around with this. So we can, for example, just switch the parsing steps off completely. And again, we get worse fit than we saw in the first case. So what we see here is that we can take this queue-based parser and that it can be combined with other aspects of memory retrieval. So in this case, of dependency in relative clauses. And even with other aspects of cognition. So in this case, the model tried to also do key presses and moving visual attention. And the resulting model can be fit very well to the reading data. And also we saw by basically switching some parts of the queue-based parser off, we could see that the parser is a needed component in the data fit. Okay, so case study 2. Okay, so we will look at Adrian Staub's study. So this is eye tracking while reading paradigm. And so in this study, what was done is that you had sentences that were grammatical, like you have in 10a and 10b, and sentences that were just ungrammatical. And they were ungrammatical, driven by this, like you had this continuation that didn't make sense. So you have like the professor saw the students walked across the quad, right? So when you basically when you hit walked, there is no way to recover it. The sentence doesn't make sense. And this was crossed with some other manipulation, and that is we either had like a high frequency verb or low frequency verb, so walked or ambled. Okay. So again, we have two types of retrieval processes. So in this case, we have sort of interaction between lexical retrieval and parsing, and we want to see how this model captures this kind of data. And what we will be modeling is eye fixations, so in particular forced parse, and regressions for the underlying three elements. So your model, so this will be one region, is over or dead. This will be the second region, ambled or walked, and the rest will be the third region. Okay, this will be the model that we will assume. So you can see that it's somewhat similar to what we saw before, but it's also not the same because now it's not self-paced reading, it's eye tracking. So we will start with attending the word, then we will retrieve lexical information, and then we will do several processes at the same time. So the model will retrieve parsing steps, and at the same time move visual attention and move eye focus. Why do we do that? So that's basically, so in this cognitive model, we implemented the assumptions that are made in reading models like EasyReader or ML. Okay, so now just a bit more abstractly, what's going on here? So let's imagine that we got into that walked or overwalked. Yeah? That's how that's somehow we got to this position. So now, so let's look at this overwalked. So we get to the context where we have, so we have over, and it's followed by the verb. And now when we look into the parsing history, because this is bad ungrammatical sentence, we are not going to find many occurrences here. So we will basically don't spread activations to pieces of information that would have exactly the same structure. We might have something like, over is followed by a noun in our parsing history, but not that much over is followed by a verb. So we will spread less activation than when we look at example like we have above that walked, where that is very often followed by a verb. So that means that in this case, we will have smaller activation, and then two things could happen. So let me just go back. So one thing is, so it's happening here, so when we are retrieving parsing steps. So one thing that could happen is basically you slow down when you are retrieving. But there's another thing that could be happening, and that is, you could actually, when the activation is really low, the model could say, don't bother, just forget about it. This is bad. And it will basically stop retrieving because it's such low activation. And at the same time, it will trigger regression. So it will say, go back because there is something wrong going on. So basically the activation of the model can now predict, it could predict regressions. And at the same time, it could, in some special cases, it could predict also a higher reading time. So this is basically like, it's a bit, you could think, if you know EasyReader model, this is a bit like enhancing EasyReader model. So EasyReader model is a model that's quite good at making these sequential predictions and also connecting reading data to sub-symbolic systems like frequency. But it cannot really connect reading data to symbolic systems like parsing. And now we basically made the link. So we can actually link symbolic systems to reading data. Yeah? So again, we do some fit. We fit here now a bit more parameters. So in particular, you might notice, I'll just talk basically about, so notice this one. This is the threshold that's basically saying we are estimating what's good threshold of saying don't bother anymore, stop retrieving and go back. And we will fit those data on reading times, namely forced parse and on regressions. Okay, here's our fit. So it's not as perfect as in the first study, but it's still quite good. So we fit, this is forced parse reading time data, and we fit the general pattern. So notice that we fit, I should say, so the bars here, so the yellow and blue bars are predictions of the model. So yellow is the high frequency data, blue is the low frequency data. And then the triangles This might be a bit hard to see, but anyway, the triangles, those are the actual observed mean reading times. And also the model actually, it doesn't have anything like intercept. It basically has to fit everything. And it fits, for example, the general pattern that, that this takes longer than this and that takes longer than that. It also fits the fact that that there's this effect of frequency on the verb where we manipulate the frequency. As I said, it doesn't have perfect fit. Yeah, we can talk about it later. And when we look at I regressions, what it does is it actually also, so one nice part that it fits is, again, it fits that there's more regressions at the last region for both cases, grammatical and ungrammatical one. But it also fits that, that regressions are, for example, so it correctly gets that the regressions will be higher in the ungrammatical case than in the grammatical case. Yeah? So it fits the general pattern. And finally, when we actually compare the parameter estimates that were derived independently in those two models, we actually see that they converge, even though they come from completely different studies. So one was self-paced reading, another one was eye-tracking reading. We actually get convergence on the cognitive model parameters. Yeah? So that's good. Okay, so we see that the Q-based parser can be combined with lexical retrieval and model eye-tracking data. And it can also be combined with things like Easy Reader and Emma to model eye movements. Okay, and here's case study 3, and here I will switch gears a little bit. So we will look at the corpus of reading data. So we will take natural stories corpus, self-paced reading corpus, which consists of 10 narrative texts in English, and there were 181 English native speakers reading the text. And okay, so now we actually will sort of simplify the model. We will only look at what Q-based parser is doing on that model. Yeah? So you'll basically take these words in the natural stories corpus. So we take the sentences in the natural stories corpus, and then we take this Q-based parser that was trained on some tree banks, open tree bank, and we will collect activations per word. And so we will know what activation each word had according to this parsing strategy. And then we want to see how well it matches reading time data. Yeah? So ideally, there should be negative match, because that would suggest that as the activation increases, then reading time decreases. So that's what the model should predict. And indeed, this is what we get. So when we look at the so here are the activations collected from this Q-based parsing model. We have various low-level confounds in the model. And so still, even when we have these confounds, when we get the activation, we get this negative effect as predicted. So basically, as the activations of these parsing steps that we have in our memory increase, then the reading times decrease. Right? So that's what the model is telling us. And we can actually look inside this model and check what is driving this prediction. So we can check, for example, is it fan size? So is it fan effect? Or is it the number of matching cues? So if you have more matching cues, you should also increase activation and be faster. And we actually see that fan size is not doing anything, so it's not significant. But matching cues are doing all the work. So it's actually, this observation is driven by matching cues. So if you have more matching cues, you increase activation and your reading times decrease. Okay, and then we can go even further and say, okay, so I started with this surprisal theory. So now we can actually take model that's built on surprisal theory and compare it to Q-based parsing model. Right? So those are basically the competitors. Right? They are trying to do something similar. They are trying to predict how our knowledge of parsing rules, how that affects processing. So I got the data from, I got these estimates from Corey Shine, and he gave me estimates for natural stories corpus using 5 gram surprisal, so surprisal using the window of 5 words. Then I'll mention this one first. Surprisal PTB, so that might mean surprisal that was trained on Pentree Bank data. So that's directly comparable to our activation, because those two, PTB, surprisal, and activation, they are trained on the same data. And then there were some other models that are not so much of interest. So there was this CG surprisal, which is trained on Pantry bank data annotated in using combinatory categorical grammar, categorical grammar rules. And then we have DLT, so dependency locality theory data. Okay, so we see that even when we add all those cognitive models, we still have, so activation collected in queue-based parsing is negative, right? So it still predicts something. It predicts speed up in reading times. And now we can actually compare, so I'll go one last step, and we can actually compare the models directly, so like which one gives us the better data fit. And we see that when we compare activation collected by queue-based parser, with this surprise log collected on the same data set, created using the Pantry bank data annotation, then we actually see that the queue-based parser has a bit better data fit than surpriser. So it beats actually surpriser. Now this is so log likelihood, we should read it like the higher number the better. So it's a bit better, the queue-based parser than surpriser in this case. Of course, I should add, so there are other surprises that were trained on different data sets, and they are even better than activation. But that's a bit unfair comparison because those were trained on, they use different data sets for training. Okay, I'll skip this slide, and I'll just summarize and conclude. Okay, so we have memory-based theories that are used to explain locality effects due to the recall of dependencies. And then we have parsing models that are explaining processing difficulties tied to construction frequency and expectations. And basically what we did here is that we went from here and used the same model, and it could do this thing. Yeah, so we go from memory-based explanation of dependencies to queue-based parsing and cover data explained by parsing models. So some things about this model. So it's an algorithmic account. And because of that, it can be easily combined with other symbolic systems. It gives us one framework for sentence processing, which can be combined with other aspects of reading implemented in ACT-R, like visual encoding. And it actually gives us very simple answer on why we would observe problems in sentence processing. And that is simply, this is just consequence of us recalling parsing steps. And when that's hard, we slow down. Yeah, so this is just like memory effect in this approach. So I think actually this sort of answer to why we observe problems in sentence processing is, for example, much more straightforward than what you would see in surprise. Okay, is this useful for you? I don't know. But what is the queue-based parser good for? So it's actually good for modeling the interaction between different types of retrieval. Right? So those were the case studies that I talked about. It's good in modeling the interaction between parsing and other cognitive processes during reading. Why? Because it's tied into this ACT-R cognitive architecture that's famous for basically being able to model different aspects of cognition. And it also allows us to basically get a window into the nature of queue-based retrieval on data that weren't used in this way before, as far as I know. So we can look at the properties of queues using some different type of data than, say, agreement attraction phenomena. Yeah. And you could try, it's possible to use this to model some other aspects, like, so I tried with some student doing local coherence or garden path data. It seemed to work fine on these type of data set. There are limitations to using something like this. So one is time and resources. So all decent models actually take a lot of time to run. So the results here I showed you, they were run on cluster computers. The parser's accuracy is not stellar, which currently I take as a feature, not as a bug, because I don't want to actually overexplode the parser so that it's basically comprehensible. I see what's going on inside it. And it is a bottom-up parser. That doesn't need to be, so transition-based parsers don't need to be bottom-up, but this particular parser is bottom-up. Okay, that's all I wanted to say. I would like to thank the research group in Utrecht that I work with, to Adrian Brashovanu, and then these are bachelor and master AI students that helped me work on this project. Thanks a lot. And in the corpus study, I didn't actually talk about it, but we also did parameter estimates and tried to match the whole reading model. And there we didn't get a good match. And I think, so there's part of the reason is that we actually tried to only predict reading times on, not at the beginning of the corpus, but some like midway. And we noticed that there are quite fast reading times in that part. So basically, the values were like higher for activation, meaning, the reading time would be shorter. So there we didn't get good match, but I think there's a reason for that. The other question was overfitting. Yeah, so that is a worry. So I think there were two things mentioned. So one was about the log likelihood. So the log likelihood only plays a role. Oh my God! Now I have to go. This will take like 1 week. Oh. So the log likelihood was only used basically for the last model, and there you could compare the models, but you can't do things like chi-square because you have the same number of parameters, right? So one uses surprise, or the other one is using activation. So there, you could do something more fancy, but I didn't try that yet. And okay, and then overfitting. Yeah, so that is an issue. And so Shravan Basish, so who was a reviewer of the paper that this is based on, he also was worried about it. So one thing I tried to do to combat that, so you cannot really split the data here because you don't have that much data. But what I did was I took out parameters from the model, and then I estimated reading times based on model and using using some so systems. Right. So basically, I would get like new predictions using the same parameters that were collected from the model. And now I'm talking about parameters like using mixed effects models, say, for the reading side. And then I tried to fit those simulated fake data using the parameters collected from, say, Gardner and Gibson, and it still got very good fit. So the model, in a way, it might be overfitting on posteriors, but the way basically it is set up, it can fit a larger set of the data than just these particular cases. So I can actually, maybe I can show you one last bit is. Okay, so one last bit is, so I also ran prior predictive checks. So these are basically checks like what you are predicting before you saw any data. And you can see that, so the model makes quite a wide range of predictions. So it predicts like, this could be up to 3000 milliseconds, some of the reading measures. So it's not like it's not super constrained as default. It might, it might overfit eventually for the posteriors. Yeah, does that help?
In the meantime, if anybody on the virtual room would like to ask a question, please raise your hand.
Hello.
Yeah.
Thank you. That was a really interesting talk. So I'm interested in, so coming from the side of sort of the surprisal theory end of things, the kind of phenomena that side of the literature likes to explore, I'm really interested in how this ACT-R type model can make algorithmic level predictions about what's actually happening, right? Whereas more rational models make a prediction at a higher level without really an algorithmic claim. So like my specific question is though, like the amount of time that it takes to parse a word, right? What were those diagrams that you showed? Sort of, can I interpret them as the little r? I think you have little r as the amount of time for each step.
Yes. Yeah.
No,
sorry, not each parsing step, but each step in those boxes.
Right.
Each box, basically.
So each like algorithmic component, right?
Each component of that whole cognitive model. Yeah. So each box, basically.
Right. So my question is, how big of an assumption is it that r is the same? That r is a constant.
So it was the same in the modeling, and you are asking whether that's weird or not?
Well, like, what is the justification for assuming that that's always the same, that doesn't depend?
Yeah,
on
so
each particular...
in a way, that was like the basic assumption. That's basic assumption done in ACT-R, that you treat it as the same. But you should notice, like, so it's just basically like so this R parameter is like fire this box. But in this box, more things could be happening because you still have to attend the word, and there will be some extra time that models this attention time. So it's not like this whole thing will take just R time. So similarly here, it will be just the R time is only fire this box, But then you still have to retrieve parsing steps, and that will be this, queue-based retrieval that will be doing that. So there will be, more time than just that. Does that help?
I think I see. So R is multiplying the time it
It's
takes.
not multiplying, it's just addition.
So so R is the amount of time it takes to retrieve parsing steps, but does that
No.
depend?
So R is the amount of time each step, basically the amount of time that it takes to fire this part, attend word or retrieve lexical information. But then inside that, like once you get into that, you will still need to do, say, queue-based retrievals. And so that will be extra time. Yeah, so it's like addition. Yes?
Hi, Umesh Patil, University of Cologne. So it's fantastic work. I really like the part where you combined it with eye movements model, and also where you model actually parsing mechanism across a corpus. So my question is connected to these two, two extremes of approaches. One is something that was taken in, say, Lewis and Wassist and Van Dyke, where they handcrafted the various retrieval mechanisms and the parsing mechanism, right? Mm-hmm. So there's one approach. The other extreme is what you are saying is you learn the parsing rules from corpus, and mm-hmm. it's more broad coverage parsing, mm-hmm. right? So both have their advantages. I mean, of course, this has advantages where you can explain eye movements data from a corpus, mm-hmm. right? But on the other hand, my question is, as psycholinguists, we are interested in specific phenomena where our theories are about specific parsing mechanism that happens in that particular phenomenon and what retrieval take place. Mm-hmm. What are different possible retrieval, what are different possible parsing mechanism. Mm-hmm. And in that case, it seems handcrafting those specific rules and retrieval mechanisms kind of implement your theory the way it is expected. Of course, you run into the problem of overfitting the data. Because
did you ever try to do this? So, I mean, did you ever try to handcraft, say, hectare model like Lewis and Wassist?
Yeah, I did.
So did you notice, so I did it several times, and I noticed very quickly that it gets out of hand very quickly. Like you basically have to decide a lot of things on spot, and like it's sort of very hard to control your process. I think also, like even if you are fair, I think it's very hard to be sort of fair and not sneak in something to fit your model. And also another thing is like it's very hard to basically replicate the findings. Like we will have hundreds of models running around here, and like each one will have its own little tweak. So this is basically like saying don't do this. So like throw this away and try to have a principled way of how you are doing parsing. And right. This is principled way that actually connects you to processing data.
Right. So what you would recommend is that just take this broad coverage parsing and whatever your mechanism is, see if the model predicts that.
So you can actually, it really depends on details of the model. But for example, when you think about, so I showed you this one example here, like, do you want to check whether active filler hypothesis works or not? You can actually do it here. So you basically just train it a bit differently, the model. Or do you want bottom-up parser or left corner parser? You can do it here, but you just train it a bit differently. But I think that's really the way to go, because then the models become comparable with each other.
So you would train it differently for different phenomena? That's what you are saying?
For different theory of parsing.
Right.
Yeah. So I would try to use, ideally, you want to use the same parsing model for all phenomena, right? It's not going to work, but
that would solve the problem of psycholinguistics. We have a model of sentence processing. That would be amazing. Yeah. But since we are not there, in the wake of time. Yeah, thanks a lot. That's amazing.